we are looking at. Now, once you have those, you can look at, you can get a sort of table, all right? So let me write down the associated diagram for this. For this example, right? So this is the decision. And here is state, expected cost, this is the expected cost due to defective atoms. And there is also maintenance cost. And here is loss of profit. And finally, total cost. All right, so if you look at those, let's see what we have here. The first one is do nothing. Now, if you are in state 0, 1, or in the first case, you can have that do nothing in either state 0 or state 1 or state 2, right? So you can be afforded for doing that. The associated cost for that would be 0, 1,000, 2,000. So I'm not putting anything new. Just if you read the description, you see what I'm doing. Just recollect all the information put together, right? Okay. And then the maintenance cost here, because you don't do anything, you don't pay anything for the maintenance cost. That's how easy it is. Now, for the last profit part, because you are still producing, so you don't have that part. So the total, you have to check the number. I thought I had a 2,000 in here. For some reason, it's 3. I think. So anyway, let's look at the second one. The second one is overhaul. Now that's only happened to state 2, and here the expected cost due to defective atoms is 0 because you don't produce anything. Once you overhaul, that will be 0. But for doing that, is the loss of profit is also 2,000. So altogether here you have $40. I will not write down the last part. You can figure that out. Here is replacement. Now that corresponding to state 1, 2, 3. And here is 0, 4,000, 2,000. So you have a 6,000 associated with this. Now, this is the information we collected for this. Now I want to basically mention what are the basic setup of the markup decision process. So again, here. So the setup is the following. So first, the state is, well, in our case, is a discrete time markup chain, but in general, it's a markup chain. It could be a continuous time as well. And so the state space, because now I'm going to expand it from the model, talk about it in general. So the state space would be 0, 1, 2, up to some capital N. And then I'm going to look at what is the associate decision. So the decision I denote by D sub I, which is the decision at state I. For example, I'm in a state 2. The machine has a major problem. Now I have to decide what to take. So the DI denote that decision. All right. And in our setup, the DI is going to take values from the set 1 up to some capital K. All right. So this is our decision variable. Everything is displayed in the slide we are going to talk about. Now, the third one is, once you choose, say DI to be equal to K, where K is one of those values in the set from 1 to K. Once this is decided, then there is a cost. There is a cost. The cost we denote that by C sum I K. So those quantities, this one denote the state, and here is the decision. Okay, so it's a function of the two variables. Depends on the state, depends also on the decision you take. The decision is from this side, where I is from the side here. It's a finite number, but there are many different possibilities. So you see, in general, the computation is quite, well, I don't know, I don't mean that complicated, but I mean it's time consuming, could be, or would be. Now, the fourth one is that there's for the Markov chain, there's the transition matrix. It's given by this. The transition matrix is given by P. Well, here, the P will be depending on K, where K is from the decision. For each different decision, you have a different transition matrix. So, say here, in our case, we have either do nothing, or overhaul, or replacement. It's 3 different things, right? So for each of this, we'll have the linear combination of those matrices associated with that. All right. So now let me write that also in component form. So very often you write that as Pijk, where here J is equal to 0 or 1 or 2 up to n. It's in the set of the state of the Markov chain. Okay, so then that's number 4. Number 5. Number 5 is a specification of decision. What you said over there is already, you have that, but here is what do you do for each of the states, for the states. So I have something like P0, P1, Pn, in general Pi. So what is the I? the I is the state. We have too many, indices. That's unfortunate. That's the Markov, basically the feature of the Markov decision process. Now remember, in this case, this D, whatever the sub, whatever here is the state of the Markov chain. In other words, it's in here. It's in the script M. Okay, so you have a decision variable, you have a state, you also have the corresponding decision. And after that, you have, this is the problem, because in the previous problem, for the machine problem, as a manager, what do you want? You want the minimum cost, you want the optimal cost. So here you have an objective function. So in general, this objective function can be, from a wide range of, ways you can choose that. But so here it's basically, those stuff what we have. Now let's go back to the example. So this is what we said, that for this, when you specify all of that, you call that a policy. So now let's go back to the example. We use that to illustrate the idea a little bit more. So I need to put on the board some tables as well. So here, back to the example. Once I'm done with the example, then you know how to solve the problem I'm giving to you later, when you get the problem. So here, the policy. A policy really specifies all the possible, decisions you have. And here, this one is the description. And here we have D0 R, D1 R, R is the policy, sorry. D2 R, D3 R. So what are the policies we have? Here we have a R sub A, R sub B, R sub C, R sub D. The first policy is, if I'm in state 0 or 1 or 2, I don't do anything. If I'm in state, if the machine is in state 3, I replace that. So replace in state 3. What about the second one? The second one says replace in state 3 overcome in state 2. If you are in state 3, you have to replace. You have nothing else to do. Now, the third policy is to replace in both 2 and 3. If you are in even major problem state, you replace that. See whether or not this is the better. Now, the last policy will be replaced in 1, 2, and 3. So any of those you replace. Only when you get a new machine, you don't do anything. So that's the decision or the policy you have. Now let's look at the corresponding policy. All right. So this corresponding to 0 state, right? The subscript denote the state. So here, that means the machine is as good as new. Now, if you are as good as new, you don't do anything. So it's the do nothing So the decision would be 1 for all of those. You have the decision 1, 2, 3. Either, this is the different, those are the state, the machine state. Those are this is the machine state, whereas those are the actions you are going to take. So here, I'm taking, if I'm in state 0, I don't do anything. So 1 denote do nothing, right? Now, what about if I'm in state 1, what I do? If you look at this policy that says replace in state 3. So if I'm in state 1, what should I do according to the policy? Nothing, right? So it's basically, once you have the policy, you have all the things written free. And here you can, likewise, you look at those, whereas the last one is 3 because you are going to replace that. You're in 1, 2, or 3, any one of them, you replace that. Now, corresponding to state 2, which is the major problem state. Now, in the first policy, again, it says do nothing, right? So you have 1. Now, in here, it says you replace in state 3, but overhaul in state 2. So here, the action is different. So I have 2, but this 2 is different from the state 2. That's the action 2, right? It's the overhaul. Now, and well, this one, what should I have here? 3? 3, right? Now, likewise, I can fill out this part. Apparently, you have no choice but to put in 3 for all of them. Right? This is the replacement. Because you are already in state 3, you have to do it. So this one is, now if you look at this looks like another matrix, right? Looks like another matrix. So, but before we do that, let's look at the corresponding transition probability matrix for each of the policies we have here. So I'm going to write down just the first 1, 2, and then the others, you can figure it out pretty easily yourself. Let's look at RA. RA is you don't do anything unless the thing is broken. So you have 0, 0, 0, 1. This is exactly the same matrix as we had before. And here you have a second A, and 3/4, 0, 0, 1/16, 1 A. 1/2, 0, 1/16, 1/8, 1/2, 0. Now let's concentrate on RB. The first column I can pretty for the first column is pretty clear. It will be the same as RA. Because you only do the replacement one that is in state 3, you move that to 1. What about the second column? Well, let's look at the second column. The first thing, this item is not changed because we don't, it's from state 0 to state 1, you do nothing. From state 0 to state 2, you do nothing. From state 3, you have this probability. So whatever the probability you have is what you have. So here you have everything will be the same as before. Now likewise for the second row, you have the same thing as before. But what about the third row? This says you replace in state 3, we already done that. We move that 1 to the leftmost, the first column. Now, what about overhaul in state 2? look at the condition probability. What should I have over there? Well, if it's an overhaul, then I should say when it's an overhaul, after that we bring that to state 1. Okay, so I should say bring to state 1. You can use in parentheses, because after you fix that, it's going to be, it's not completely as good as new, but it's still good, so it's a minor problem kind of thing. So here you put 1 here. And if you put 1 here, it's a condition matrix. The other rows is all, the other elements are pretty much decided. You cannot have more than 1 in a row. So this gives you that quantity, right? So the last, well, what about the last row? The last row is also very much decided because this is 1, the other is these. So it's pretty easy to figure out what the condition probability, right? So when it's overhaul, you bring that to state 1, so that becomes 1, all the others becomes 0. Likewise, you can get RC and RD. Okay, so then what is the problem next? Next, for this one, we need to find steady state probability. For this one, we need to find steady state. For this one, we need to find steady state. So you have 4 different steady state probability associated with that. Then after you've done that, what do? You compute the corresponding long run average expected cost for this. And then you compare those values, look at which one is the smallest one. The smallest one turns out to be the optimal one. Okay, so is that okay, or did I do too fast, or is it okay?
Can you just finish this example?
I'm sorry?
Can you finish this example?
Yeah, here I did calculate the stationary distribution for this, right? Likewise, you can compute the stationary distribution for this. You can compute the stationary distribution for this and that. Then you compare all of them. So here, I will get 0, 0, 1, 1, 7, 8, 3, 4, 0, 0. 1, 16, 1, 16, 1, 8, 1, 8, 0, 0. And here, this one is 0, 1, 1, 1, because all of them are replacing. And only the first row is unchanged. Now then you can compute the stationary distribution corresponding to each of the condition matrix. So you will have 4 vectors, 4 stationary distribution vectors. How do you compute that? Exactly the same as before. You do pi times p equal to pi, and the sum of the component of pi